In these first situations, we use the Fleming hand rules. Left rule is for the motor effect and the right rule is for induction. In this particular case, the current would flow left to right conventionally, therefore the electrons would flow right to left. The force due to the current in the wire must oppose the direction. Otherwise, you would get an accelerating effect when you just started a little bit of motion, which would completely contravene your conservation of energy. So the force is against the motion that's inducing the current in the first place. Question 34 is relatively straightforward, just use EMF equals BLV. Question 35 uses the same equation, E equals BLV. Because B is constant, L is constant, and V is constant, your EMF induced will be a constant. So the first graph, we get a steady EMF induced in one direction, followed by a steady EMF induced in the opposite direction. So that we get a square cut graph that swings above and below the x-axis. Second situation, we get a slow velocity in, so we don't get very much EMF induced, and then a very rapid and opposite EMF induced as we pull the wire quickly back out. Final graph, there's no perpendicular direction, so it's 0. Question 37 is an interesting one about Concorde flying through the Earth's magnetic field. Quite a common type of scenario, so it's good that you get this practice. And you have to realise the Earth's magnetic field is very variable around the Earth. At the poles it's very strong and perpendicular to motion that's horizontal to the surface, whereas at the equator it's the opposite. The Earth's magnetic field at the equator is virtually parallel to the Earth's surface, so you get very little induced EMF around equatorial regions. Okay. For part B, we just use EMF equals BLV. All the values we have, we just have to be careful with the prefixes and make sure we sub in the correct powers of 10. And we get a relatively small but measurable EMF induced. Finally, part C. We have to go back to thinking about what the magnetic field is doing around the Earth and when are we actually cutting through it. And the places we're not cutting through it is at the equatorial regions where we're sort of flying parallel to it. Question 38 is a good example of where we don't have a metal rod moving perpendicular to the field at all times because it's circular, so we have to consider the average. So we need to know our velocity initially at the tip, but then we take half of it to find the velocity halfway along the radius of the blade, and we use that average velocity to apply to our equations. And then it's just as before, our EMF equals BLV, and we take the average velocity but keep the full length of the blade. Question 39 is just applying our flux equations. So we haven't got any coils, it's just literally what's the area of the pitch and what is the perpendicular magnetic field to it. So it's understanding it's the perpendicular magnetic field through a certain area. So we have to resolve to the vertical. Question 41 is a good one because it's quite obscure. We've got this rectangular metal square in a magnetic field and we move it about and we can flip it over, we can move it left and right, up and down, etc. And what we're interested in is looking at the change in the flux. So you consider where it starts and where it finishes, And if you get the same flux through both areas, then there effectively isn't a change in flux. Okay, so part B1, there's no change in flux. If you move it the same to the right, you just get exactly the same answer as you started with, so therefore there's no flux change. When you move it outside the large rectangle of magnetic field, we get a change in area of half, so it goes down to 7.5 milliwebers. Part 3, again, no change in flux. Part 4 is a good one, where we're flipping it over, but we're sort of going to the halfway point, and it's going from there for maximum flux magnetic field through the area, so maximum flux to zero flux, because when you turn that rectangle vertical against the magnetic field, there's no area perpendicular to the flux, so we would get a change of 15 milliwebers. And finally, for part 5, when we flip the rectangle over, we've effectively flipped the area from a plus area to a minus area conceptually. So we've got 15 milliwebers in one direction, and then we flipped it over, so it's 15 milliwebers the other way, which gives us an overall change of 30 milliwebers. So that's where that comes from. The last part, part 6, we literally just lift the rectangle up above the magnetic field, but the magnetic field is still perpendicular to the paper and still through that rectangle. So the final answer is also 0, because we haven't changed the magnetic flux at all. There is no change, there's no difference. We haven't turned the rectangle over, and we haven't let it leave the area of magnetic field. So there's no change in the flux, so we get a 0 difference. Question 43 is an excellent question, and it's very commonly used by the English exam boards, where you drop the magnet through a coil and we produce this classic EMF graph. It's just Faraday's law and Lenz's law in action, and you have an accelerating magnet. So as the magnet falls through initially, the magnetic field cuts through the coil, and the top of the coil will be induced as a south pole by Lenz's law. It'll try and stop the magnet falling. Through the middle of the coil, we get sort of a 50-50 situation, so it swings through 0, and then as it falls out of the coil, it is falling faster, so you get a larger EMF induced, and you get the bottom of the coil becoming a south pole because it wants to try and stop the magnet falling. If we look at the graph, you can see the acceleration of the magnet into the coil, peaking at A, and then as it falls out, a greater peak at C, and you can see that the time interval for the A part is longer than the time interval for the C part, because it's falling slower to begin with. So part B, if we remove the data logger, which is a high voltage, it's like a voltmeter, and replace it with just wire, we now have a current flowing in our coil. And if we have a current in our coil, we have an electromagnet. So the induced current from the magnet falling through it creates an electromagnet itself within the coil. And this is where Lenz's law really starts to apply. So your induced current, due to the EMF that's induced, will oppose the motion of the little magnet falling through it, which is making it in the first place. So that's why initially we have a south pole at the top of the coil as it tries to stop or repel the magnet falling into it, and then it switches to trying to attract it back in as it falls through the bottom and stop it falling. So that's force. You've got this magnetic force that's opposing the gravitational force, and therefore your resultant force is going to be smaller. And if your resultant force is smaller, your acceleration is smaller. So it won't fall at g, acceleration of gravity, it will fall at something smaller than that. So it's slower. The whole process is slower if you allow current to flow in the coil. If you don't allow current to flow in the coil, then you won't get this effect. You'll just get the readings for the EMF. If we think of it in terms of energy, we have potential gravitational energy turning into kinetic energy. If you allow current to flow in the coil, that is effectively creating electrical power within the coil, and that would become heat. If you did it often enough, you'd get measurable heat in the coil. So our potential gravitational energy is turning into kinetic and electrical energy, and therefore your kinetic energy can't be as high from your initial gravitational potential energy according to the conservation of energy. And therefore, if your kinetic energy isn't as high, your velocity can't be so high. So it falls more slowly if current is allowed to flow in the coil and you get a conversion of kinetic into current electricity. Current electricity that could actually do work. The work it'll do is it will heat up the coil. If we look at part C, our Faraday law states that the EMF induced is equal to the rate of change of flux linkage. So flux linkage is dependent on the number of coils. If we double the number of coils, we're going to double the EMF induced. So your peaks would be twice as high. You wouldn't get any change in the velocity because it's falling under gravity, and that won't make any difference to the time. Part 2, if we make it twice as high, we have to think of equations that link velocity to height. Two obvious ones are our equations of motion or using energy. Both show you that v is directly proportional to the square root of the height. If we double, square root of 2 is 1.4. So your peaks would be about 1.4 times as high as they were previously. But we're also falling faster, which means that you're going to get the whole process happening more quickly. So your time interval between peaks will be shorter. This is a relatively straightforward question. We're just subbing in the values we're given in the question. And it's just sort of your interpretation of the numbers. You're told the area, but you're told it in centimetres square, so you need to convert that into metres square. You're told the magnetic flux change or the magnetic field change in a second. So we just use 2 and divide by 1, as in 2 Tesla and divide by 1. Part 2 is simply Ohm's law. Question 47, nice, slightly obscure question, but totally doable. So you're looking at the area, you're looking at the magnetic field, and you're looking at the number of coils. And then they tell you it changes from its maximum, so a 75% change within a period of 0.4 seconds. So that allows us to use Faraday's law to work out the EMF induced. Question 49 takes a little bit of thinking about. It's quite obscure. But what we're using is our force equals BIL equation initially. And we're thinking, well, if that force acts on it and you have to pull through it, then you have equal and opposite forces on the wire. So if you wanted to move at a steady velocity, you have to apply the same force as it's trying to stop it, effectively. So you're thinking Fleming's left-hand rule. We know that power is force times velocity. We also know that power is current times EMF, or current times voltage. We know conservation of energy, and that equals conservation of power. In other words, the energy per second. We equate the two equations, and then we cancel out I, sub in the force part, and we end up with your EMF induced is BLV. Question 50, we have to realise that when we say ideal, what we mean is the physics is perfect. So we're not sort of dealing with wasted energy, we're not sort of dealing with those kind of real world factors that apply. And therefore, the power on the left-hand side of our transformer should equal the power on the right-hand side of our transformer, which is quite easy to show. In other words, the efficiency is 100%. So the P of our primary equals the power of our secondary. And we have the current and the voltage on either side. And lo and behold, they both equal the same amount, 48 watts. Question 51, we have a little transformer system. They tell you things like the power, the output voltage, and the coil ratio. So we're just applying our equations, our transformer equation, where we have our voltage ratio the same as our coil ratio or turns ratio. And we find that the input voltage is 240 volts. If it's a perfect transformer and 100% efficient, then our power on either side is the same. So therefore our input current would be 0.1 amps. And the power must be the same as well, so 24 watts. Question 52, same sort of situation. You're given a step-down transformer. You're not told the coil ratios at all, the turns ratios. You're given the two voltages, and they ask you for the ratio, which is 10:1. Part B, you have to calculate the current in the projector lamp, which is just basic electricity equations, P equals IV, and we get 10.4 amps. And finally, if you have 10.4 amps, you would go to the fuse that's above that value, and that's the 13 amp fuse. If you go lower, you risk the fact that it will probably melt at certain times during use, whereas if you're a bit above, you're safe. Finally, question 54, again, just using our transformer equation, we need the output turns, so that is NS, or our secondary turns, rearranged, sub in the values, and we get approximately 113 or 110 to two significant figures. If it's 100% efficient, our power of our secondary equals our power of our primary, so I times V is a constant for either side, and substitute in, you're actually told the output power was 60 kilowatts, and therefore you would have a current of 5.5 amps in the primary side. Finally, 5 bulbs of 100 watts each, we'd 500 watts, same physics, same scenario. We would only need 0.045 or 45 milliamps.